almost for a matinee today, which is actually really incredibly lucky because Eugene Cordero has been involved with climate change meteorology, but also activism and all kinds of interesting research and practice in conceptualizing our locus of control at the individual level for a problem that is a global scope. So he's a really, really neat person to be able to spend some time with. And everything that he does can be expanded and multiplied by you as you go out to your classes. So if you've not yet seen him speak, it's a real treat, and we are lucky to have him visiting us from the meteorology department. Eugene Cordero.
Thank you very much. So it's really nice to be here, and I'm excited to share with you some of the work that I've been doing, and also to answer any questions you have or to discuss with you. I don't have many answers. This climate change topic is very complicated. There was a fantastic article in The Guardian today, which I think was titled, How Can We Deal with Climate Change and the Economy? And it's a long, in-depth article. The editor for The Guardian, who's retiring in a few months, has decided that the last 6 months of his tenure is going to be devoted to climate change because this is the most pressing issue of our time. And that was a fantastic article. So I'm going to talk to you a little bit about the research that I've done and some of the also education and social change type of work. But I'll be really interested in your feedback, and anytime you have a question or anything, obviously it's pretty informal here, so I'd be interested in your feedback and your questions. I know most of you know quite a bit about climate change, but I'll just talk about some general things, and then hopefully this will provide some area for us to discuss. Obviously, the increase in carbon dioxide is one thing that's changing in our climate system. And, our goal is to see if we could change this trajectory, ultimately. Because as we put more heat-trapping gases in the atmosphere, things change. So my research is going to, so I have two pieces to this talk, actually, that's here. I'm going to talk about the background about climate change, and then I'm doing me and my grad students are doing some work on this hiatus. And if you're not familiar with this, I'll explain this hiatus. And then I'm going to talk a little bit about the Green Ninja project. So here's the global average temperature of the planet for the last 120 years. And the red line is the 5-year running mean. But you see the temperatures bounce around quite a lot from year to year. And in addition to temperatures changing, we know that the amount of Arctic sea ice is also changing. This is a NASA image of the amount of sea ice. And this is what was normal in the 70s and 80s, and this was in the year 2012, which was a low year. And here's a chart that shows the extent of sea ice over the Arctic, and this is for every August period. And you can see that there's a trend. 2012 was quite low, and then it recovered for a couple of years. But there's this kind of variability, and that's one of my research interests, is why some years higher than other years. I did want to briefly look at this because I think that even in our community, even in the atmospheric science community, some of this we take for granted. Like, how do we know what is causing recent changes in climate? In fact, it's not intuitive. Just because we see all this pollution going into the atmosphere doesn't mean that natural changes, like changes in the sun or volcanic eruptions, might be playing a similar role or larger role. In fact, this volcanic eruptions, there hasn't really been like super big ones recently, but there's been moderate ones. I don't know if you remember a couple of years ago, there was one in the northern part of Europe, and they closed down a whole bunch of air traffic because of this volcanic eruption. So as scientists, we're trying to evaluate, okay, what impact does changes in the sun have? What impact would volcanic eruptions have? So really, what is the evidence of a human connection? And in some of the fields that you study, you probably are aware of tracers for human chemicals or human activity. It's equally challenging in the atmosphere from a climate perspective, to say for sure, okay, this is from humans. But there are some ways. So I'm going to share with you a couple basically lines of evidence, that have convinced the scientific community, or my scientific community, that humans are playing a role. And one of them is called radiative forcing, which is an energy bookkeeping type of exercise, and the other is using climate models. And the reason I'm talking about these is both of these, we use both of these in my research right now. So this is a very, very busy chart, and if you haven't seen it before in a class or just on your own, it might seem a little overwhelming. But if you want to talk to, let's say, a physicist or an engineer who doesn't believe that climate change is real, and there's plenty of them out there, because physicists think that they're the top level of the scientific community, and so if they haven't discovered it, it's not real. We had this recent case of this Berkeley physicist who didn't believe that climate change was real, got funding from conservative groups to reanalyze all the surface temperature data, and then, oh wow, discovered that all the surface temperature data was correct from NASA and from the European Center. And now he's even saying that humans are responsible. But he had to do it himself, and his group had to do it themselves before they really felt it was true.
Do you know, what's his name? You remember? I'll look it up. I know his name.
Yeah.
It was like 4 years ago or something.
Yeah.
No, it was
Yeah.
recently.
Yeah.
There was another one that had to flip up in Berkeley about 3 or 4 years ago.
Yeah, it's escaping me, so it'll either come to me later or eventually pull it. But this is a great tool that you can use to educate yourself and also to educate others about the fact that we're keeping track of every watt per meter squared of energy that comes from the sun and where it goes and how it reacts and interacts with a whole bunch of other things. And so,
Mueller.
Yeah, Richard,
Yeah.
Richard Miller, I just thought of.
Go ahead.
and he got some other money from the Koch brothers to fund him to reanalyze surface temperature data.
Probably lost some friends, huh?
Yeah, because they were convinced that it had to be wrong. The temperature of the planet can't be warming. And in fact, it was nice. They did an independent analysis of data and also found identical results. And then his funding is dried up. At least he was true to the science and didn't just fake it and say, oh, no, you know. So what this chart does is it looks at how different processes, different things that have changed on our planet, like the amount of CO2 in the atmosphere, the amount of carbon monoxide or aerosols, have changed over the last 250 years. And then it determines what impact does that have on the radiative budget for the energy balance of our planet. So if, like for example, carbon dioxide has gone up in the last 250 years, that causes extra energy, and this is a scale from 0 to 3 watts per meter squared, positive or negative, which means this would warm the planet and this would cool the planet. And so if it's a positive radiative forcing, like for carbon dioxide, it means the planet's going to warm. And if it's a negative, like due to these aerosols, that means it's going to cool. And here's an example of something that I always think about. You're driving your car, and you're driving your car along, and you know CO2 is coming out of the tailpipe. But of course you can't see CO2, right? It's invisible. What do? You see all this junky stuff coming out of the tailpipe. Some of that junky stuff are aerosols that actually cool the planet. So it's actually not intuitive for you to know whether the warming effect of the carbon dioxide or the cooling effect of the aerosol, which one is winning. The only way to know is you have to do the calculations yourself. You have to figure out how many cars and how much CO2 and how much aerosols and how long they live. And you have to do a real scientific analysis. And that's what these folks have done, is that this is a real scientific analysis of looking at all the factors that warm the planet and all the factors that cool the planet, and then to see which ones win. And then also you can compare it to other things like changes in sun. I don't know if anyone's noticed, but it's getting a little sunnier out there right now. It's not a lot, but the sun is going through its normal progressions like many stars. It's getting brighter and brighter and brighter. It's about 30% brighter today than it was 2 billion years ago. 30% is a lot. If we increase the sun tomorrow by 30%, our planet would, it couldn't adapt, but it has adapted over the last 2 billion years. So it's getting stronger every year, just a tiny amount. Is it overwhelming climate change? Well, according to these calculations, changes in solar radiance are causing the planet to warm by 0.05 watts per meter squared every year. We can measure it, we can identify it. How big is that compared to CO2? Well, tiny, but it's still something as scientists we want to measure. So what we found after doing this analysis is that the planet was warming due to anthropogenic activities in the 1950s, in the 1980s, in the 2000s, and it's getting larger. So we can quantify And also what's interesting and I find exciting about this is that this allows us also to see if we want to reduce climate change, what would be the most impactful way? And potentially what could be an economic, could you figure out a way to increase these aerosols, for example, to cool the planet, and what would be the economic consequences of that? That's something that some people call geoengineering, may not be what some of us think is the best idea. It might be better to reduce the warming factors here. But ultimately, there will be a carbon trading scheme. There will be money associated with all of this. So if you can figure out ways to change some of these things, you might be able to run a business or make some money doing that. So this is one methodology that has convinced the scientific community that humans are contributing to our changing climate and are the dominant one, especially since the 1950s. The other way is through climate models, very similar to weather forecasting models, that this black line are the observations. And then when we put in the anthropogenic changes, human changes, and natural changes, we find that the models can actually well simulate the observations, which are in black. So this is a simulation from the year 1890 to 2000. They're initialized in the year 1890. They run forward and they change the amount of greenhouse gases every year. They put some volcanoes in there. And they really pretty accurately reproduce the observed temperatures. But if you take humans out, if you pretend humans didn't exist and you didn't have the increases in greenhouse gases and the increases in aerosols, these are the model simulations. And they're just way too cold by the end of the century. They can't reproduce the warming of the last 40 or 50 years. Which is why in the IPCC latest report, they say that the majority of warming is caused by humans over the last 50 years. That's where some of that comes from, is that up to this period, that the models seem to be fairly similar. And so maybe humans weren't playing such a large role. But especially in this last 30, 40, 50 years, the humans are playing a much larger role.
So the non-human warming percentage you would describe as what number?
Well, if we were to say that all of this piece here, that the humans were playing a very large role, then it might be 0.2 degrees here, then another, it could be like 20 or 30% or something. This might be part of a natural cycle.
So we're talking about less than 1%?
No, we're talking about
No, I said that natural.
Yeah.
So you said most. It's
Well,
always interesting because,
okay.
in response to, there's natural things too. And I'm like, yeah, but they would be excellent.
Okay, so most of the warming in the last 40 years, that most, it's going to be 90% or something.
So 10% natural.
Yeah, maybe at the
Okay,
most.
right.
And you're just using something like this as a guide, or these models.
Well, that's what I was picturing, is
Yeah.
that little.
Yeah. But there's so the sun's getting a little stronger, there may be some other, actually it leads in well to what I'm trying to understand, which is the kind of research. So let's go back to this diagram. And I like to share with my students that every year, this is the annual temperature for the year, this black line here. And this year was pretty hot, and then this year got cold, and then it went bounced up. It's a bit like a pinball machine, it's kind of like bouncing around. And I'm interested in why it bounces around so much, especially if you look at the last decade. And this is what some people call the hiatus. The fact that the planet since about 1970 was warming pretty steadily, and then over the last decade seemed to stop. That's this word hiatus. And in the skeptic community, climate change skeptics, and there's plenty of them out there, although they don't happen to publish in the scientific literature. 97% of scientists publishing in climate journals agree that humans are responsible for our climate system changing. But in the internet world, and if you just type climate change on Google, you'll find that about half of the first sites that come up are skeptic sites. And there's probably reasons. But they love talking about, this is an area that says, hey, why is the planet not warming anymore? We're putting more CO2. Every single year we put more CO2 in the atmosphere. And yet, over this time period, it's flattened out. Although 2014 was the warmest year on record. You can see that data point here. But it's still, there was still a flattening. So what is causing that? Now, one analogy that I like to use is this walking a dog. I don't know if you've seen this before. There's a nice little video on YouTube on this. You can kind of picture what happens. But anyhow, just imagine yourself and you're walking your dog, or a dog, and so these are your footprints. And I'm heading to the store. And me and the dog are going to get to the store together, right? Because your dog's on a leash here. But this is the footprints of the dog, or the paw prints. And you know the dog sniffs something over here and gets curious over here. And so, in a way, this is a bit like our climate system, is that we know that based on the forcing that we are moving in this direction. But the weather and the natural variability of the climate system actually meanders quite a bit. And it moves up and down. And so that's kind of, when we go back and look at the actual temperatures, we see this meandering. Now, the research question that my grad student and I were trying to answer is, does the climate system look like this, where this evolution of our temperatures, the temperatures are moving up and down, whether that in a way, the leash on the dog, whether it's small or whether the leash is quite large. So, going back to even this diagram, my question is, how long is this leash? Like, how far can the climate system differ from its initial, or from the trajectory or the trend? So, so that was the basis for our research question. And of course, we're interested in that because when you go back and look at the temperatures, and is this normal, or is there something we don't understand? Because we had these other periods too. We had actually a cooling period, and then it went up, and then it flattened. So it's not just a systematic, like CO2 goes up and temperature follows identically. It doesn't quite work like that. So in order to do that, we what we did is, and this is, the idea is pretty straightforward, but it's a little bit complicated in practice, is this is the observed, and this GMT means global mean temperature. So we took the global mean temperature, that's in black, and then we basically tried to fit it with, in this case, a polynomial that's based on forcings and some volcanoes. And we were able to reproduce the observations pretty well. And then what we did is we subtracted one from the other. And that subtracted, the residual, is an estimate of the natural variability, or how the Earth's climate shifts naturally. I'll give you an example of why the climate system shifts. For example, when we look at this black line, it goes up and then it comes down, it goes up and comes down. Anyone have an idea why one year might be warmer than the other? What could cause the Earth? And it has nothing to do with humans.
Well, there's like El Niños and
Yeah.
volcanoes and.
Could be a volcanic eruption, could be an El Nino. In fact, El Nino, La Nina do have quite an impact. Whenever there's a strong El Nino, the global average temperature goes up, just for that year. And whenever we have a La Nina, which is the opposite, it tends to cool. Now that's not intuitively why that would be, but what happens is warm oceans come closer to the surface, they kind of touch with the atmosphere and warm the atmosphere during El Ninos. So El Ninos, volcanoes, maybe the sun got a little stronger, those are all things. And going back to the pinball analogy of the climate system always bouncing around, that stuff is always happening. And El Nino is like a 1 or 2 year thing. There may be other things that are like 10 or 20 year things. Like the ocean might get a little bit warmer for 10 or 20 years and then cool down. That's all part of a natural cycle. And so this
Sun
thing,
cycles are about 20 years too, right?
sun cycle is about 11 years.
11
yeah.
years? Well,
There's
11 up, 11 down?
Oh no, 5 out, 5 and a half
Oh,
out,
okay,
5
okay.
and up down. So there's a solar cycle too. So this then is an estimate of all those other things, the sun and volcanoes, and that's what this residual is. And so if the climate system matches, this is a pretty close match. This doesn't tell us anything too much. But if here's the observations again, but then this yellow thing is more like what the forcing looks like, what is really causing the climate system to change. And this is really just a linear trend. It's basically just like taking CO2 and then adding volcanoes. But when we look at the residual, we find out the residual is pretty large. And what that means is that this isn't probably how our climate system really works. Or that if it does work this way, there's lots of other things going on that are natural. And that's what we're trying to identify. So it's these, we're trying to determine what's we call it internal variability. What's this El Nino and ocean cycles, how are they affecting climate system? So we use past observations to try to develop an understanding of what is the normal background climate variability. And so this is a very busy plot of the last 800 year, or the year 1000 to 1800. we get this from tree rings and ice cores, mainly tree rings. And this is how the temperature changed. And in this point, we're assuming that humans weren't really involved in this. So we can use this to determine what does the background really look like without humans. And this is all we call them the radiative forcing. These are all the things that caused the climate to change during those past times. So there were volcanoes, there were some changes in greenhouse gases, not because necessarily of humans. There was solar, and then there was land use. Humans were changing what the land looked like. And those are all things, mainly we're causing the planet to cool. There's some warming factors too. So then we can take this and basically subtract this to get the residual, the kind of, what does the pinball machine kind of look like without humans, without any other forcing involvements. And this is an estimate of what the natural cycle is in our climate system. So that sometimes it'll cool and then it'll warm, and then it'll cool and warm. And we developed a model to simulate this, to simulate the properties of this, so that we could apply the background state to many, many climate model simulations. And we could do it thousands and thousands of times so that we could establish kind of a probability distribution, or to use statistics. So we could say, we understand how the background works, and now let's apply it to the last 100 years or to the future. And then this is an example of that. So that we take a climate model and we run it for 100 years. We don't have any humans in there. This is the model running. And then we look at how unusual are these occurrences. And that's what the shading here is. It's telling us at the 95% level or 97 or 99, how likely are some of these things to happen. And one reason we do that is that we look at what happened in the last 100 years. And we found that this warming that we saw in the last 50 years could not have happened by chance without human activity. It's another way of validating this. So, so this is the last slide on the research that I'm going to show you. But what did this tell us? Well, and I know that these are busy charts, and I'll kind of skip forward. One thing this told us is that that when we go forward over the last 100 years, that the temperatures can only be reproduced if we include the human contribution. But this is looking into the future. This yellow line is the observations, and then these other colors are simulations of the future. And what we find is that we are still, even though we had this hiatus in warming over the last 10 years, the temperature didn't go up much, we're still within the kind of probability that it's not super, super unusual for us to have a 10-year or 11-year hiatus in warming. It's getting to the 95th percent level. This is with a high emission concentration, but it's not completely unusual. In fact, we quantify it even more closely. But we are at the low end. If we were to stay like this for another 10 years, if it doesn't warm anymore in the next 10 years, then we'll know, we'd be out here, outside of this, and we'd say, no, it is strange. I'm not sure why that's happening. Maybe we need to rethink our science, or maybe there's something else going on that we're not paying attention to. We know the greenhouse gases are causing warming, but there must be something else going on. But we're not there yet. And in fact, we developed this chart that looks at the future that says, what's the probability of having a trend that goes for 10 years and that's negative? And if you had a trend of minus 0.05 and it was 10 years, what's the probability of having a cooling trend for multiple years? And so that's what this chart basically illustrates. And these are the last 11 years of this is the chart of the recent temperatures. And that's probably most clearly illustrated here, is that the chance of at least one occurrence of a trend of 11 years, that's what we've just experienced, 11-year cooling trend or negative trend. Depending on the emission scenario, whether in the future we put a lot of CO2 in the atmosphere or not much, but if you put the middle level, that's about a 50-50% chance that you're going to get 10 or 11 years where it doesn't warm. Now for us in this field, that's important, because let's just say that you go back to the observed temperatures, which are this yellow line here, and it doesn't warm for like 10 years. Some people are going to say, hey, climate change is not real, or we don't need to do anything about it, or you guys, environmental scientists, are always saying stuff, but it's not, look, it's not really happening. So from the scientific community, what we're saying is it's not that unlikely that at least once in the next 50 years, we're going to have a 10 or 11-year period where it doesn't warm. That's part of the natural cycle. That's not that unusual. So that's what we learned from this. In fact, depending on how much CO2 we're putting in the atmosphere, it might even be like a 70% likelihood that you're going to get that. It's going to then catch up again. Remember the guy walking the dog. We're going to get there. But that leash could be longer than we had initially anticipated.
Do you know like where we are in the cycle right now? If it's like warmer right now or colder right now we're in that cycle?
Well, we are, if we look at this yellow line here,
Yeah.
we're just in this 10 or 11-year period where it's been flat.
Okay.
Now, there are some other longer-term cycles, like there's a sunspot cycle, which doesn't have a big effect on temperatures. There is an orbital variations, which should be pushing us into kind of very, very slowly, but into a cooler phase. But what we expect to happen is we expect to kind of catch back up.